Hello, I'm Michael Frank from Sandia National Laboratories, and I'm going to talk about our recent work on exploring the ultimate limits of adiabatic circuits. Just as a brief outline, I'll give some one-slide motivation this subject and a little bit of history. I'll talk about our approach focusing on our development of what I call fully adiabatic CMOS circuits. I'll review our progress to date and give some teasers of early simulation results from our project and mention our test chip layout. And then I'll talk about next steps for this effort moving forwards. Okay, so very briefly, the motivation for this whole line of work is something that we call Landauer's principle, which is a fundamental physics that tells you that there's fundamentally an upper limit to energy efficiency for the conventional digital computing paradigm, which I call the non-reversible paradigm, in which we are continually overwriting information and effectively doing it. It turns out that physics dictates that time you erase some known or correlated information without regards to the knowledge you have about its state or its correlations. This implies that you have to dissipate energy to the environment. And the amount of energy is given by K log 2 for each bit's worth of information lost. So that's a very rigorous, and physics tells us that the only possible way around that limit is to use what's called reversible computing, which involves avoiding these kinds of erasures. So we take care not to lose information in a computation. And in principle, if you do this, energy dissipation per computational operation can be made as small as you like. We can approach, theoretically, zero dissipation per operation, which means you could theoretically approach unboundedly large amounts of useful computational work performed per unit of energy that's invested into the computation. You know, to make this practical, it takes a lot of work. Some of the important milestones were Bennett showing in 1973 that in principle any irreversible computation could be embedded into an equivalent reversible one. The first serious attempt at engineering implementations was Konstantin Likarev's work in 1977 on reversible superconducting circuits. And in the 80s and 90s, various people worked on adiabatic circuits in CMOS. And an important milestone there was Unison Knight's CRL, or charge recovery logic style, 1993, which was the first fully adiabatic sequential CMOS logic. And my fellow students and I in Knight's group in the late 90s, we fabricated several complete processor chips through MOSIS using adiabatic circuits and reversible computing principles. So I think the time is right currently to make some new demonstrations and create a resurgence in this field looking forwards. So just very briefly, a little about adiabatic using MOSFETs. The idea here is that we're approximating charging with a constant current by using a voltage source that ramps up gradually over some time t. And when you do that, you find that although the dissipation is still 1/2 CV squared for a very short rise time, as the rise time increases, you approach this adiabatic scaling where the dissipation scales down in proportion to the ramp time. And so because of this, in principle, the dissipation can be made as small as desired, modulo leakage, and I'll talk a little bit later about reducing leakage. One observation, though, is that to connect this with reversible computing theory, you have to generalize the theory of reversible computing because this circuit is only conditionally reversible. It's reversible if this transistor is not turning on or off while you are performing a transition through that transistor. And so there's a whole paper here which you can look at about how reversible computing theory has to be modified to accommodate those cases. An important thing in any practical adiabatic circuit is to recover energy from the circuit, and you need a resonant rail driver to do this. In principle, this can be done by using the Fourier decomposition of whatever waveform you want. And for this case, we want a trapezoidal waveform. And it turns out that with a 6-component Fourier series, you can approximate that to within a couple of percent. This is an exaggerated display of the error from ideal. And so we're designing circuits at Sandia that actually achieve this. So there's some specific circuit techniques which I don't have time to present. We have a couple university collaborations. One of them with Karpur Shukla at Brown University is exploring the fundamental physics of reversible computing to try to provide a solid foundation for more advanced engineering of devices and circuits looking forwards. And then we have a collaboration we're trying to start up with Tom Conti and Andrew Jain at Georgia Tech, investigating architectural implications of improved reversible technologies. So those are both just getting started. So in terms of our progress at Sandia, we've been building circuits and simulating them using, oops, let me go back, using this logic style that I call 2-level adiabatic logic. It's essentially a slight generalization of the original CRL logic style by Eunice and Knight. These are dual rail transmission gates. And this particular architecture lets you implement a reversible shift register. It uses 4 different clock phases. And in general, for a fully adiabatic design, you have to follow certain design rules for maximal efficiency. The circuit should also be fully static. And here is a fully static variant of 2-Lao that was recently invented. It turns out to require 8 clock phases, but we believe that it can be more efficient as a result, that you can essentially approach arbitrarily low energies with this modulo leakage, which I'll talk about. So we have been simulating these circuits in various processes, including our in-house processes at Sandia. We've been using a number of pretty conventional simulation tools for this, including SPICE-based tools, as well as technology CAD physics simulators for evaluating new device structures. And just as a snapshot of some results we're releasing at this time, for a relatively arbitrary operating point of 1 megahertz clock frequency and 10 femtofarad interconnect capacitance, we get a dissipation for 350 nanometer technology of 37 attojoules per 800 nanometer width for the devices per clock cycle. And in the 180 nanometer technology, we get 7 attojoules per 480 nanometer width. And this second data point is comparable to one that we got for the TSMC 180 nanometer process in an earlier study at the University of Florida back in 2004. So I consider that earlier result to have been adequately replicated. So these results are not optimal. If you sweep over the parameter space of frequency, VDD, and body bias, I believe you could do much better than this. But we haven't completed that part of the study. We have, however, taped out a test chip. This is a 720 stage register in Sandia's 180 nanometer process, and we hope to by its functionality and empirically measure energy dissipation. So some important near-term next steps include further optimizing our operating point for minimum energy, implementing the newer fully static version of 2-Lao, to develop our oscillator design, exploring other candidate implementation processes, perhaps some MOSIS runs, and possibly developing an open source cell library so that the broader community can more easily play with these technologies. And for the longer term, the energy efficiency for fully adiabatic circuits is limited only by leakage, and so you have to aggressively reduce that. One way is to use older processes, which have exponentially lower leakage, but of course the energy delay products are not as good. So to make things more cost efficient, we'd like to use newer processes, and one way is to operate them at cryogenic temperatures, which steepen the subthreshold slope significantly at very low temperatures, and therefore leakage, subthreshold leakage can be reduced by many orders of magnitude. And if you re-optimize the device structure, you can excuse me, also reduce gate leakage. You could explore superconducting resonators and superconducting interconnects, and we believe that the combination of methods like this should allow a cryogenic optimized process, if operated using our design styles, to beat the energy efficiency of any other semiconductor process that's been demonstrated to date, and by quite a bit as well. So in conclusion, we believe the limits of energy efficiency achievable in adiabatic CMOS are very far away still. And in fact, no fundamental limit to that is yet known. There are a number of requirements, though, to continue to make progress, such as using fully adiabatic logic styles and make them fully well, design high-quality resonant oscillators with trapezoidal wave shapes, and minimize leakage aggressively. I believe in the long run, the energy gains achievable using these methods will create a demand for 3D stacked chips, which reduce interconnect overheads. As that demand increases, it will cause a reduction in cost per layer and per device. And so overall costs, including both time amortized per device manufacturing costs, as well as energy costs, can continue improving. And so I think there's a bright future for computing if we explore these techniques, and doing some exploration of fundamental limits can yield further breakthroughs in terms of efficiency. And in conclusion, if we design things right, then we can gain vastly more efficiency, but because of Landauer's principle, these vastly more efficient computers of the future will have to be reversible. And that's it. Thank you very much.